Record, and then I'll put you on mute. So if you got any questions, just go ahead and just speak. Just keep it quiet. If you got any questions, go ahead and speak up. Then right. So first of all, we're in unit 1. So I'm using this right here. So you go to unit unit 1, the resonance and the actually not this section here, but you want to go to. Let's go back a little bit. So we're going to want, I think it's the second to last section of unit. Get back out of this. I'm just going to use another student here. He's in the same course. I'll click on that section. All right, so too far. And all right, so this right here. So again, hopefully everybody's used this, and Matt, I'm going to guess you're probably using this again. And this really, like it happened for last semester for you. If you use these, fill these as you go, makes a big difference. Okay, so there's some pages has, let's say, 6 total pages, a little longer than usual. Okay, so I'm gonna hit some basics of this really quick. What I kind of based my little lecture here on is the mass test. I looked at the mass test and kind of base things on that to help you out mass test. Okay, so I'm gonna look at my notes here. So first, what are beats? Well, if you go to slide 16, 17, I can jump there real quick. Let me get out of this. And again, all the information should go in the guide notes in the same order as the slides are. So the first question, the mass test, actually is based all the way over here to slide 16 and 17. When it starts to ask what beats are. Again, a beat is actually a place where you have, of course, you guys covered constructive, destructive interference. If you have constructive interference, would actually overlap 2 different waves, say a flute and a guitar in the picture right there, that's a beat right there. Okay. So a standing wave is also standing waves real quick. Any standing wave is any wave in a medium that actually they have the same frequency but travel in opposite directions. That's part of your mass test. Also, there's a question that deals with this right here. So to have standing wave, 2 waves coming toward each other, they have the same frequency and again in the same medium, either both in the air or both in water, perhaps. Okay. We get into beats again. Beats again are going to be down here. I think it talks about it. Down here someplace. Yeah, right here, called beats. So the sound has to rise at points of constructive interference right there and falls at points of destructive. So when it gets louder, you have constructive. When you have destructive interference, it's going to get a little quieter. Okay. And the periodic and repeated fluctuations in the intensity of a sound due to interference of sound, either destructive or constructive or destructive, is going to be called beats. And the overlap, the constructive, call that a beat. Okay. And then slide 17 talks about that a little bit down here. We have 2 guitars. I don't know much about playing guitars, obviously. I don't know if you do, but if they're up by 1 hertz, 441, 440, you get a different effect. So they had a different beat at that point. Okay. So again, constructive interference occurs at points where the ripples meet in the same phase. Destructive actually where they're a little bit opposite, a little off. Okay. Okay, so that's what beats are. That's one of your questions. Then a short video for you guys to watch here. Let me go to here, YouTube. A little more detail. Make sure my sound's turned up all the way. Before I play it, hold on. Stop my share for a second, make sure my sound turned up. I do not. Just a second. Here we
go. Here are 2 identical tuning forks, both marked 288 Hertz D. If I sound them together, you can hear that they're making the same note. They're in agreement. But what if I put one in ice and the other in a flame? I'll tell you in a minute. These 2 tuning forks are not in agreement. This one has a little extra mass so that it lowers the frequency slightly. Now if I sound them together, you'll hear them interfering. You can see the effect on an oscilloscope. Now that the forks are ready, let's have a listen. First to the cold, and then to the hot. And then together.
So you beats.
Can you hear the interference? When two frequencies are very close together, they add rhythmically, both constructively and destructively. The result is called beats. Beats, a rhythmic interference of close frequencies. Quiet, loud, quiet, loud. Wow, 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 wow. When people tune pianos, they often listen for beats as the notes get closer and closer. Beats aren't just about sound waves. They explain why ocean waves seem to come in sets. Surfers notice that waves come in sets. That is, small waves, then big waves, then small waves, and so on. Now that's a wave interference phenomenon. Sets are a type of beats. So watch out for beats.
Good enough, right? That dude is too cool for school. All right. Let's get out of so my next thing, Doppler effect. There are questions with Doppler effect in your test. Let me see which slides those are on. Well, actually, it should be pretty quick here. Let me stop share. Make sure I'm sharing the right thing now. Hopefully you're not too bored yet, Madison. Okay, so Doppler effect. Doppler effect, you can watch these videos and yet when things come towards you, they seem louder. If somebody's talking to you, they walk towards you, it seems like louder. But when they go by you, it seems like it's a little hard to hear what they're saying. Like you walk away from me, I can't hear you. All right, so or like you always know, sirens come towards you. It's like a fire truck. It's really loud. Once it gets by, it's quieter, and the frequency changes. The frequency really changed, but it appears to change because it's a moving source of sound. Okay, so we got a little video I have for that. Wrong thing here. Let me see. Am I? Yeah, I actually got a video for that in my. Stop sharing this. Let's go to my other share. My website, once again, which is here. Again, my website, you guys, there's also alternative activity. So Madison, when you do the Unit 1 activity, if the animation thing or the tool doesn't really work, just do this right here. Click on that, and they'll an alternative activity. Just upload that to the activity itself, and be a lot less hassle for you. So I'd recommend. That's why I like Physics B better than Physics A. It's not really any harder, but I think it's actually easier than what we had for for Physics 1. So the activities shouldn't be too bad for you. Especially Unit 2, you have optics. Make sure you do this alternate activity here. It's like the actual activity, but it's more explanation there, more detail, and it's a little bit less too. So it's not that bad. Kids really well on that. So anyways, off topic. So here's my waves gonna get started. So when our standing waves are, there's both these videos here. You can watch those. Let me go with Doppler effect, which I had. I didn't save it, so let me go real quick to find it. Find a short version of this. And this might be the one right here. Let me shut it down. There it goes. Commercial first.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
True.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch, and then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got some.
So yeah, redshift, and it's all stars have redshift. And so at least it appears all stars, including our sun, are all moving away from each other. Galaxies moving farther apart and everything. So, all right, good. Let's go to stop sharing that. Okay, so you're gonna see the question about that, the Doppler effect on your in your MASH test. That's what we're talking about. Next, there's at least two questions, Matt, about Doppler effect in your MASH test. So nodes and antinodes. A little bit for you guys to watch here. Now, at least one question will have a question 4 is going to talk about which one's a node. So let's see what nodes are. Let's go to here. Hold on, I'm not sure if I'm sharing this or not. Hold on. Okay, let me share this with you.
A stationary wave occurs when two sets of waves of the same amplitude and the same frequency, which are propagating in the same medium but in opposite directions, overlap.
Yeah, get that? Let's play it back a little bit. That's the question you're going to see. So listen carefully to that one, what she just said. If it plays.
A stationary wave occurs when two sets of waves of the same amplitude and the same frequency, which are propagating in the same medium but in opposite directions, overlap.
So everything's the same, sets going toward each other in opposite directions. So same frequency, same amplitude, in the same medium, both in light, or both in the air, both in the water. Okay, moving on.
In a stationary wave, each point of the wave performs oscillations around the position of equilibrium, but the amplitude of the oscillations depends on the location of a given point. The points, known as antinodes, oscillate from a position of equilibrium to a maximum distance which is equal to twice the amplitude of the overlapping wave.
So basically, antinodes are the very tops, okay? The crest or the trough.
The points known as nodes, however, always remain in the position of equilibrium. All other points perform oscillations with an amplitude which is lower than the maximum.
There you go.
A
Oops.
stationary wave occurs.
Okay, good. So antinodes are going to be at the very tops and nodes right in the middle. So when the question will ask you how many nodes are there going to be, okay? So how many places the wave actually touch the flat line, the horizontal line, okay? Okay, moving on. Let me see. And then destructive interference. Again, constructive interference is when two waves at again over the same frequency, same amplitude, overlap on each other, and that makes it louder. Okay, we're talking about longitudinal waves or sound waves. Okay, and then a little more about standing waves are real quick. Let's go to this. Hold on, am I showing that or not? Make sure I am. There we go. Right one. And this one I want. Okay. Here you get different standing waves. Like again, we're right here where there's pretty much flat. It's like called a node. Up here, those are antinodes. Look, just one single wave. You got standing wave right here, but each string, okay. Well, there's just one string, but that's your antinode node. You have 1, 2, 3. But if you change the frequency, you can change the number of nodes and antinodes. Again, so the waves overlap one another. That's pretty cool. So the more higher the frequency, the more nodes you get. Okay, good. Next, what else we got to know here and cover? Resultant. Okay. If you have waves of resonance has resultant waves of when you have resonance, we'll have let's actually show a video about that result. So actually find the let's get out of that real quick. Please have that window. Good. Let's go to resonance real quick here, actually. Gotta go back actually. Resonance. Resonance is back here. I believe this shows resonance here. I don't want that one. I guess we could. All that's showing is if you have the right frequency, and then you have every object has natural frequency. If you can reach a natural frequency of an object, in that case, that glass, you can make it shatter. You can actually make it to resonate or vibrate. Okay, let me check something real quick here. That little video for that I should call it, but maybe I didn't. Let's go this. Okay. So one thing just know for your test, you're going to ask what is you have resonance. Okay, you're going to increase the natural frequency of an object. Okay, so if you have resonance, it means the amplitude of the waves actually overlap each other. You get constructive interference, and that's what we call a resultant wave. When two waves overlap in resonance, you get a really large wave. Okay, when that makes it louder. And then that video showed you something called fundamental frequency. So when you have the lowest frequency you can have to actually produce a standing wave. What the heck, let me get a video for that I was going to show you. I'm just going to website real quick so I can find it there. I might already put that in there. Let's see, one more video. I'm going to stop streaming this one and go one more video. It should be right here off my website. Here we go.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 115, Appear to Stand Still. And so an example of a sound standing wave is the waves found inside a vuvuzela. And so you blow on it, You get that sound. You blow it with a higher frequency, and then you could even try to pierce your lips a little bit more and get an even higher frequency. But what's happening is you have these specific standing waves that sit within the chamber of the vuvuzela. Now, a wine glass works the same way. If you rub your finger with a little bit of water around the surface of it, what you can do is generate these standing waves inside the wine glass. What you're doing is vibrating the sides, and as you do that, you're vibrating the air, and since you have a standing wave inside there, it makes this pitch. Add water to it, and you're going to have a slightly different pitch. And so waves can either be traveling or standing waves.
Yeah, a little water and try a wine glass. Try it real quick. And then add a little water. It is pretty quoted in my class 10 years ago.
Traveling waves will move from one place to another, and standing waves will appear to stand still. Now, when you look at it, it's kind of an illusion. They're standing still, but the traveling waves are bouncing back and forth. In other words, they're being reflected off the boundaries, and then there's interference to create these standing waves. And so if we look at this animation, the dark wave is going to be the standing wave, but in the background you can see the blue and the red waves that are bouncing back and forth and back and forth, and it's the summation of them that creates the standing wave. Now, if you notice, that standing wave is going to have areas where it's not,
so you call the big wave right there, the blue wave, the resultant wave of the two,
moving at all. And that's due to destructive interference, where the waves are canceling each other out. And we call those in physics nodes, areas where it's not moving. And then we're going to have total constructive interference in certain areas, and we call those antinodes. That's where it's moving the maximum amount back and forth and back and forth. And so an example of this could be found in instruments, for example. So a string, it's fixed on each.
Jump ahead a little bit.
A tube, that's going to GT are moving out the door, and then they've moved on forever. But if we add a boundary on the other side, in other words, if we add a fixed boundary, you can see now there's a reflection back. So those waves didn't just keep going, they bounce back, and now they're going to bounce back again. And as that wave goes back and forth, you can see that we're starting to generate these standing waves. And you can even see those nodes and those antinodes. In other words, those areas where it's not moving and those areas where it's moving quite a bit.
So yeah, 4 nodes, 4 antinodes there.
So this is an animation of standing waves, and so what we're doing is as the blue wave moves to the right, becomes the red wave, which moves back to the left, and it just keeps going and going and going. We're getting destructive interference. That's creating these antinodes, where those two waves add together to make a much bigger. Hit the ball. Sometimes you'll hit it and the bat will kind of buzz in your hands. In other words, it vibrates quite a bit. And the reason why is that you're hitting the ball on an antinode, an area where the waves going up and down the bat are actually constructively interfering to create a huge vibration there. And we refer to it as the sweet spot, the spot on a bat where the node is, where you don't have much vibration, that you hit the ball and you don't feel really any vibration at all. And so let's go through experimentation. So this is a SimBucket simulation. What we're doing is, so an example on one side. In all these words, there's no net movement on either side of that string. If we look at an instrument like a tuba or a vuvuzela, what is the characteristic of that? Well, we're vibrating it, but you can see that on the left side,
jump out a little bit.
Characteristic of a standing wave in a chamber that has two open ends, it's always going to be an antinode on either side, but depending on the frequency we can get different pitches as we blow through. Rubens tube is a really cool example of that. In a Rubens tube, what you do is you fill up a chamber with gas, a gas that's flammable, and so this guy's lighting the chamber, so we're having flames coming out of the top. But on a Rubens tube, you put a speaker on the side, and what that speaker does is create these longitudinal waves. Those longitudinal waves, as they move through, will create areas where there's a lot of compression, and in an area where there's a lot of compression or antinodes, then the gas really can't make its way out, and so it'll be really low there, but at the nodes it'll actually come out quite a bit. And so did you learn to predict the properties of standing waves? They result from reflection of these traveling waves. Could you collect data? Again, I use the SimBucket for standing wave.
There you go. Yeah, Rubens tubes are really cool. Okay, let me see. Anything else to cover here for this section? Yeah, there's no fundamental frequencies. The lowest frequency you can get to actually create a standing wave. You just got to reach a minimum amount of frequency to actually make something start to vibrate, basically like a glass. Just right frequency, just enough to make it start to vibrate a little bit. Okay, so I'm going to put some of these videos. I'm going to update my website a little bit so I can put more stuff in there, and then I'll next week try to produce a reviews guide like I used to make. and put that in for unit 1. Okay. Mesh, any questions at all?